continuing with our exploration of momentum, and today we're going to look at collisions and explosions. Sounds quite violent, but it really isn't, okay? It's a really nice section. So let's just remember where we've been, okay? So what we're going to think about in this section is, why does a rifle move backwards when you shoot it? So you shoot it, you know the bullet goes forward, but if you don't shoot it properly, it can do a lot of damage, okay, especially big rifles. So, but why? Why does it have to move backwards? You can't actually shoot a gun without there being recoil, okay? And also, when you have ice skaters that are on ice and they push against each other, why do they go backwards? Why do they move apart? What is it that causes that? These are all things where we're now going to investigate how that works. So we're looking at these with the rifle, that's an explosion. The ice skaters are also an explosion, but we could have a collision there as well. With the way I ice skate, it would be a collision, but we're not going to worry about that. So remember, we've worked through a lot of this already. So we've done the definition, the equation, properties, Newton's laws, change in momentum. Today we're going to look at the conservation of momentum. All right? Keywords, things you need to take into, that you need to remember. I'm just going to do this, I've got this all the time. There we go. All right. We're going to look at the word isolated system. You should have heard this term before, but I'm going to go through it in detail so you know. We're then going to look at the conservation of momentum. You should know what conservation means because you've heard it in terms of energy, and we know what momentum is, so we're going to put the two concepts together. And then we're going to look at collisions that could also be explosions, okay? In this section of work, when we talk about a collision, we could also mean an explosion. They go together. It's the same type of situation, okay? So, there we go. I've got the explosion. Sometimes I get a little ahead of myself. Now, let's look at conservation of momentum. So first of all, what we're going to look at with this is we need to define what an isolated system is, okay, because it only happens in an isolated system. We then need to talk about what do we mean when total momentum remains constant. Remember, we're dealing with vectors. And then, with the total momentum remaining constant, we're going to consider the size of the total momentum and the direction. Now, that's something new in terms of your conservation laws. You haven't done a conservation law yet that involves a vector. You've only done one that involves a scalar, which is energy, okay? So here we're going to have to put our thinking caps on so that we can keep track of what's happening with the direction, because momentum's a vector, so direction is very, very, very important. Okay, so what is meant by an isolated system? So first, let's split this up into what the words mean, okay? So when you hear the word isolated, what do you think of? So if we say somebody is at home isolated, okay? Or they stuck in the middle of the ocean and they're isolated from everyone else. What do we mean? We mean they are on their own, okay? They're alone. So we would look at it, so from an English point of view, we would go, they're alone. They're the only thing that's there. So if I'm talking about an isolated system, I'm taking a system and putting it on its own. So I'm taking all the factors around it and I'm ignoring them. Okay, I'm taking them out of the equation. A system is just the situation we're talking about. So here we're talking about collisions and explosions. So when we have two objects colliding, or one object exploding, that interaction between the objects, that's my system. And I'm taking it from the big picture, so from everything that's hanging around it, and I'm only going to consider the small little section. That's the system. Okay? So let's define it nicely. A system is defined as a small part of the universe that we consider when solving a particular problem. So, we know the universe is very big. If we try to consider a big part of the universe when trying to look at a collision, wow, the maths and all the other things that comes into play would just be way too difficult. So we narrow it down to just the objects, the things that are involved in what we're doing. Also, at this level, we ignore a lot of extra factors because we don't quite have the maths yet, okay? And that's fine, because at school level, we're trying to teach you the foundations. We're giving you the principles so that when you go study physics at varsity, at university or college or whatever, you have the foundation that they can then add on to, okay? By an isolated system, this is now the important definition. It's one that has no net external forces acting on it. Now, I haven't just said net force. We know what a net force is. It means that an object will change its motion. When we have objects colliding or exploding from each other, they're definitely going to change their motion. But I've been specific here and I've said external forces. What I'm talking about here are forces like friction. Okay? Friction's an external force. So we're ignoring friction. We're going to say, no, we're not going to worry about friction, simply because when we look at two objects colliding, we're actually only concerned with that little moment in time when they do collide. So the friction they may be feeling on the surface they're on, it's so small and for such a short period of time that, well, we can ignore it. Okay, so here, an isolated system means no net external forces. You have to use the word external, because there are going to be forces in the system. All right, so because when the objects collide, one object's going to push on the other. Newton's third law. Those forces can't disappear. Otherwise, the objects won't change their momentum. All right? So, what do I mean when I say total momentum remains constant in size and direction? Size is easy because we can calculate the momentum of the objects before anything happens. We can calculate the momentum afterwards. And magnitude's easy to compare. Direction, though, is something new. And direction is very important because we're dealing with vectors. So when I calculate the momentum of my system, originally, that momentum has to have a direction. It has to be going somewhere. After something happens, the momentum total needs to be the same, and the direction needs to be the same. So when I first do this, if I say that it's going to the left, it must finish going to the left. It can't change direction, because then something's gone wrong. Okay, it's just one of those things with momentum. It's quite easy to prove, but it's got to be constant in size, magnitude, and direction. Okay, so this gives us the principle of conservation of momentum. This they love to ask. Total linear momentum. I've underlined total linear because it's the thing you leave out in your exam. You'll tell me that the momentum of an isolated system remains constant. No, we've got to be specific about what in the momentum. So it's the total. Now, we generally only use 2 objects, but it could be 3, it could be 4, it could be 700, heaven forbid, okay? But the word linear is very important. We only deal with momentum that happens in the same plane. So generally, it's going to be horizontal, okay? So we'll have 2 objects moving horizontally towards each other, and hitting or exploding from each other, but they have to be in the same plane. So I can't have one coming down and the other one going sideways. They don't go off at angles. Okay, we don't do 2-dimensional momentum. Even though we don't do 2-dimensional momentum, you still have to put the word linear in your definition, okay? So this principle says to us that the total linear, by using the word total, that means size and direction, remains constant. It doesn't change. When it comes to the equation, we're going to spend more time on this just now. I'm hoping you've seen the sigma sign before. That sign means sum of, okay? Sometimes we'll write this as total momentum before. So if that's easier for you to write instead of the sigma sign, because it's got to look like a sigma sign, it can't be an E, all right? You can also write it as total P after, and I'm just going to go up there. All right. So we're going to deal with that soon and how we work with that, okay? So we've had a bit of an introduction. Lots of things to think about. We're going to take a short break, and when we come back, I'm going to show you how these collisions work. So I'll see you in a couple of minutes. Welcome back. So you've had a chance to think about what we spoke about before the break. Now we're going to look at some stuff in detail, so we get to the exciting part, okay? So what we're going to do is we're now going to investigate what happens when objects collide, okay? So there we go. So here we have a simulation, and I've set it up, number 1, so that you can see the vector diagrams, okay? So this is the momenta diagram. We've done vector diagrams, okay? 2, I'm going to play around with these 2 objects, okay? And what we're going to look at is we're going to see what happens to this when they collide, okay? So that's very important. I'm going to see if I can make that a bit bigger for you. There we go. So at the moment, my 2 objects aren't moving. We're not going to worry about the time. At the bottom, I've got a whole bunch of stuff, so I can already see that the momentum of my first object is 0.5. The momentum of my second object is minus 0.75, okay? We're not going to worry for this part how we calculated that momentum, okay? Because that's not what I'm trying to show you. What we're doing by default, I can't actually change it on this, is that we're taking to the right as positive, okay? That's the default. That's what we're going to work with. So let's press play, okay? They bounce off, and away they go. So now, okay, what I want you to see is a couple of things. Number 1, they came together and they bounced off. So they changed direction, but they remained as 2 different objects. I'm going to reset. Now, over here, when we look at the momentums, if I add the 2 momentums together that I've got here, it's 0.5 plus minus 0.75. So my total is minus 0.25. That's that tiny little one over there. I'm going to let them collide again. Oops, there we go, before it disappears. I'm okay that they've changed. Now if I add my two momentums together. So I'm going to go 0.38 minus 0.63, and you know what? It's minus 0.25. The total's still minus 0.25. That little momentum vector for the total didn't change. And it can't change because momentum's always conserved. I'm okay with the fact that the object's momentum's changed. Okay? That's fine. They need to change by the same amount, basically, but we'll talk about those later. Okay? We will definitely deal with the change in momentum with each one later, so don't stress. So this first one, they come together, they collide, and then they move apart. So that's one option of what can happen. Let's reset this. And what I'm going to do, okay, now we're going to do one slightly different. So I'm going to change this velocity. I really am. It will let me do it. No. Okay, let's change. I'm going to change this velocity. There we go. So what I'm doing is I'm making the original velocity. It's like, it's wanted to get it to naught. There we go. I wanted naught. There we go. I'm making this stationary. So now we have one object that's stationary, and we have another object that's moving. Watch with my totals. Number one, still, let's take that velocity vector out. It'll be easier. Still 0.5. None for number two. So my total momentum at the moment is 0.5 kilogram meters per second to the right. Let's let them collide. Oh, now what happened? They collided. Number one went backwards. Okay, so it bounced off, and the second one started to move to the left. Oh, no, to the right. That's that way, to the right. Okay, so one was stationary, one hit it. As a result, the one went off and the other went off in the opposite direction. Now, if I look at my totals, number one now is minus 0.25. Number two is 0.75. If I add them together, I still get positive 0.5. Still positive 0.5 to the right. Momentum didn't change. Okay? Let's reset it. Let's change it so that we're going to have this one. I want this one to be going to the left, to the right as well. So I just want to make sure I've got it going to the right. So we're just going to do that. Okay? Let's take that away. We're now doing the situation where both objects are moving in the same direction. This can happen, you know that. So if we think about in cars, it happens quite often, where somebody bumper bashes somebody else. Okay, so the car in front's not going fast enough, and the other one hits in. Okay, we know it all happens. Let's see what happens. Now, first of all, let's do the total. So we have 0.5 and 0.65. That's 1,15. Okay, I'm doing it quickly in my head. You guys can do it on your calculators, okay? But it's positive, so it's to the right. So let's see what happens. Oh. Now when it bumps off, number one, its velocity decreased significantly. Number two, sped up. It's like a bumper car. Okay, so it got faster. Now you're going to tell me, Tracy, something's gone wrong. Because if I add these two together now, I get 1,14. But when I reset it over here, my total is 1,15. I haven't lost momentum. My simulation can only give me accurate values to 2 decimal places. So there's probably decimals missing that if I then add them in, I'd still get to 1,15. Don't stress about it, okay? we'll often find when we're doing experiments that maybe we don't get 100% correct. It's experimental error. It's okay. The general feeling here, though, is that they are equal. Okay, so just watch again. So they go, okay. Now, we can also do, no. Can you see I'm thinking? It's sometimes hard. All right, let's change the mass here. So let's make the masses equal. All right, so that we can see whether that makes a difference, because momentum is about mass as well. Okay, so let's try this one. Here my total is 0.72. Let's see what happens. Oh, look, it's 0.72. But did you see something very important? Watch here. Because the masses are equal, number 1 is going at 0.5 for its momentum. Number 2 is 0.22. Watch when they collide. Number 1 is now 0.22, and number 2 is 0.5. Basically, they transferred their momentum to each other. What if they're going in opposite directions? So let's reset this. Let's change this value. Okay, so let's change that value to minus, let's put it as 1. Okay, so let's move it a little bit. So now what I've done is I've got two objects that have exactly the same momentum in size, but opposites in direction. Can you see total momentum is 0? Each one has individual, but because they're vectors, they cancel, the total cancels out. Let's see what happens. Oh, look at that. They have to spring apart, okay? They have to spring apart. But we do get situations. So now what I'm going to do is I'm just going to change this here. I'm going to reset, okay? Let's see what happens if I make it an elastic collision. Total momentum still 0, but now we have the option that they're going to stay stationary. They're going to stick together, okay? But they can stick together while moving as well. So let's change. Let's make number 1 bigger this time. So I'm going to make it 1 kilogram. Okay, so number 1 has a momentum of 1 going to the right. Number 2 has a momentum of minus 0.5. So number 2 is going to the left. My total momentum is to the right. Okay, 0.5. So let's see what happens. They stuck together. So the first ones we were looking at was they bounced off each other. Don't worry about the elastic, inelastic at the top there, okay? We'll deal with that next time. But they became one object. This also happens regularly, okay? We often have objects so they collide with each other and they stick together. But what happens is the total is the same now. I also need you to see something. When they stick together, they both end up with the same velocity. They're one object. I can't have them stick together and then you tell me, well, the first one's going at this velocity and the second one's going at this velocity, but they're not the same. Not physically possible. They have to stay together, okay? Now, unfortunately, this particular simulation doesn't allow me to do an explosion, okay? So with an explosion, they will start as one object and then they move away from each other. They have to move in opposite directions. It's not possible for them to move in the same direction. So we've looked at the simulation. Let's now put this in a way that makes sense because we've got the equation and we need to write this equation in different formats. So this was total momentum before, so I had one object and its initial momentum is m1 plus vi1. We had a second object All right, so that gives me the total momentum before the collision. Afterwards, we had one option where they were separate. And this is the option you're going to use most of the time, okay? Where the two objects are separate, so you're going to work out all their momentums separately, okay? We then also had, further down the line, we had the option where they became one object. So all that changes is this. Before they were two, so they both have their own momentum. Afterwards, they become one object, so we add their masses together, and we have a single final velocity. All right? You can still use the first equation if you want to when they stick together, but you have to remember that their velocities are equal. So sometimes it's just easier to add their masses together. The other option, which I couldn't quite show you, is if they start as one object. So that means we would go m1 plus m2, and they have the same initial velocity, and afterwards they have two different, I'm telling you, I put a 2 there and it should be a 1. Oh my goodness, that's a 1. And that's a 2. Okay. These aren't equations on your information sheet because they derived equations. They're ones we have to make up, okay? Make up in inverted commas. We have to look at the situation. So writing down what we know becomes very important here. When we do calculations, we're going to use one of those three, always. But we'll do it step by step. Lots to think about. We're going to take a short break, and then we're going to apply what we've learned. So I'll see you in a couple of minutes. Welcome back. So we've done a lot today, okay? So we have spoken about conservation in a lot of detail. Now we've got to put it to practice. So we're going to do a couple of questions. Hopefully, as we do the questions, I'm going to be able to help you read through the questions, because the theory is not difficult. I just personally feel that sometimes it's about understanding what they're asking you, okay? So let's look at the question. We have a ball of mass 350 grams. So that's our first situation. Now, we can't work in grams, so we know this is going to be 0.35 kilograms. It moves on a frictionless table, yay, makes life easier, at 2 meters per second to the left. So this is the initial velocity of ball A. So I'm going to call it VIA. Ball A, strikes ball B. So now we've got a second object, and that one has a mass of 200. So we know that that's 0.2 kilograms. And it's traveling in the opposite direction with 1.2. So in other words, B is moving to the right. Okay, and that's the initial. Then they say after the collision, so they hit each other, ball A continues in its original direction at 0.7. All right, I showed you a situation where they could collide and they keep going, end up going in the same direction. Now they ask you, what is the velocity of B after the collision? Now we go, wow, lots of information. How do we process this? The best way, if they don't give you a diagram like here, is to draw a diagram, okay? And by a diagram, I don't mean it has to be a work of art. Don't spend 3 hours on it. It's just a sketch. So they said to us that I had ball A, here's ball A, going at 2 meters per second to the left. Then it meets ball B, which is going at 1.2 meters per second to the right. I know that this is 0.35 kilograms, and I know that this is 0.2 kilograms. Then the collision happens. You see, it's very exciting. It's 2 lines. Afterwards, we don't know what happens to B. Okay? So I'm going to leave it. That's what I'm looking for. They tell me, though, that ball A continues in the same direction. I now look at this and go, logically, ball B should be going to the left. Ball B needs to change direction. For it to keep going to the right, somehow it's got to jump over ball A. Not going to happen. If you don't see that, it's okay. It'll work itself out in the question. But I'm looking at the problem and going, what do I expect in my answer? What do I think the velocity is going to be? Right. So, now we need to set up our equation. I'm going to need to rub out my diagram because of space. Okay, so I'm going to take this away. You've all got it. Also, what I need to do is make a decision about direction. I'm going to take the first direction that was given to me as positive, and that was going to the left. So anything going to the left will have a positive velocity. Anything going to the right will have a negative velocity. My 2 objects were separate at the beginning, and they are separate afterwards. They didn't say to us that they become one. So do not make that assumption. We might find out that they have the same velocity at the end. Then they became one. But they didn't tell us that. So don't make that assumption. So we have to start with the total momentum before is equal to my total momentum afterwards, where I have the mass of A, the initial velocity of A, plus the mass of B, and times the initial velocity of B. Afterwards, we're going to have the mass of A with A's final velocity. We're going to have the mass of B with B's final velocity. Now we substitute in. We've done the science, actually. So, 0.35. A was going to the left initially, so that's positive 2. B is 0.2. It was going to the right, so it's negative 1.2. Afterwards, A's mass hasn't changed. It's still going to the left, so it's still a positive 0.7. And I know the mass of B. I just don't know the velocity. We now have a math sum. We've done the science, okay? The next part is the maths. So the majority of your marks right there, okay? And this would normally get you about 3 marks because it's a mark for the equations and then a mark for the substitution on either side. Now we need to solve for B, for the velocity of B. If you can solve straight away and not show all the maths, please do that. That's your choice. It's not a problem. We don't mark your maths. But I'm going to show you all the maths just so we're all on the same page, okay? I'm going to solve the left-hand side first, so I'm going to need the calculator because, well, it's important. So let me put it over here so I can see what the sum is. So I'm going to go 0.35. There's my other bracket, times 2. Then I'm going to add to it 0.2, and that is times by minus 1.2. And what do I get? Fraction. We can't use a fraction. It's positive 0.46. Okay. Oof, There you go. I think you can read that. Now I'm going to do the other side. Okay. So let's put this over here now. Okay. And we're going to go 0.35 times 0.7. And that gives us 0.224 plus 0.2, which means I need to take the 0.224 over, so I'm going to minus that on both sides. I'm not going to write it down, so we got 0.46 minus 0.224, and I get 0.236. That's equal to 0.2 times the velocity of b. So now I divide by 0.2 on both sides, so I can keep that answer. And I'm going to divide by 0.2, and I get 1.18. And it's positive, okay, which I knew was going to happen because when we discussed this, it made sense to me that it would keep going to the left. Okay, so this has just meant that I was on the right track, but we're not done because it's a velocity. Velocity requires me to tell you which direction it was going in. Okay, that was quite a nice question. Momentum is always conserved, so it's using the same equation over and over again. This is definitely a section where you practice, you practice, you practice, you practice, and you remember direction, okay? Let's do another question. So we have a soccer player who kicks a ball, which has a mass of 0.45 kilograms east. Now I'm using east, at a velocity of 9. This is an interesting question. Now I say to you, the ball enters a container of 0.2 kilograms, lying at rest on its side. The ball becomes stuck in the container, and the ball and container now move east. Then they say to you, calculate the velocity of the ball container system immediately after the collision. We definitely need a diagram, okay? Because now we're going, oh wow, they give me a ball and they give me a container, and there's just all this stuff going on. Let's draw a diagram. So we have, okay, a soccer ball of mass 0.45 that's going 9 meters per second east. Okay, I'm going to make that to the right east. Then there's a container that's sitting on the floor. Whoever kicked this ball is amazing, because I wouldn't get it in the container. That's 0.2 kilograms. It's stationary. When the ball goes in, the container and the ball become one object. So the ball goes in the container, and because the ball was moving, the container and the ball moved together. They want to know what is that final velocity. So really, by drawing a diagram, we've made this a lot simpler than it sounded. And that's the important part here. That's why we draw diagrams, okay? I'm quite visual, so I like to see what's going on. Plus, it helps me with direction. So when I look at this and I go, well, actually, we only have one direction, which is east. Brilliant. It means I don't have to worry about negatives, because it's a logical choice that east is my positive direction, okay? So let's solve the question, okay? My total momentum before is going to equal the total momentum afterwards. So before the collision, now what I'm going to do is we can use M1, M2, etc. But we've got a ball in a container, and sometimes we need to try and keep track of which one was 1 and which one was 2. So I'm going to use subscripts that help me. I'm going to use a little b for the ball. Okay. And for the container, I'm going to use a little c. Please, just because the container isn't moving and it's stationary, so it actually doesn't have a momentum, you can't leave it out the equation. You have to show it to me. All right? It can't just disappear. Afterwards, they one object. Okay? So let's just quickly remind ourselves of the values. So if we go back, the soccer ball was 0.45 and it's going at 9. Okay. Oh, look, hang on. I've missed something. If you look carefully, it's very important to read your questions properly. Okay. Or, of course, forget the fact that you've got silly things over there that it wasn't supposed to be there, okay? And that's fine. So, 0.45 going at 9. The container was 0.2 times 0. Okay? Afterwards, they stick together. Ooh, maybe I should write a plus instead of a multiplication. There we go. Now we need to solve for f. Now it's a maths problem. So let's do the first part, which is 0.45 times 9. I can't do that in my head. So 0.45 times 9 gives me 4.05. I'm not going to worry about the 0.2 times 0 because I know it's 0. Okay. If you need to put everything in your calculator, please put everything in your calculator. Then I'm going to add the two masses together. So 0.45 plus 0.2, which gives me 0.65. Solving for VF, I now divide both sides by 0.65, so it's going to be 4.05 divided by 0.65. Whoop, yeah, there we go. And we get 6.23, 2 decimal places, okay? So VF is 6.23 meters per second. It's still positive, so it is east. I expect the final velocity to be smaller than the ball's original velocity because the total mass has increased. Okay, and the momentum's got to stay the same. So if the mass increases, velocity needs to decrease. Otherwise, the momentum will change size, which is not something we can do. Okay, so what have we learned today? Well, we've learned that the principle of conservation of momentum says to us that the total linear momentum of an isolated system remains constant, which then means, and I've just written it slightly different, that total momentum before equals total momentum after, and we will have to derive the equation that makes sense for that, for the circumstance, for whatever the question gives us, okay? That brings us to the end of today. We did a lot. You need to think through it. And next time, we're going to do conservation of kinetic energy. So I'll see you then.